Yeah, let's get started. So yeah, I'm Alex Bienstock. I'll be chairing the first session of today on private information retrieval. I think we have a few very nice talks. So let's get started with Yunhao Wang, who will be talking about snake eye resistant PKE.
Good morning. Thanks our chair, Alexander, for the introduction. I'm also glad to see you here in this section. My name is Yunhao Wang. I'm going to present our work, Snake Eye Resistant Public Key Encryption from Learning with Errors Assumption for Oblivious Message Retrieval and Robust Encryption. I know this is a long name, but I will gradually introduce all the terms. And then this is a joint work with our wonderful collaborators, Zeyu Liu, Katerina Sotiaki, and Iran Chomer. Before I go into any technical details, I will first give us a motivation. Imagine that we have an anonymous message delivery system with a sender and a whole bunch of recipients. Our goal is for the sender to send a payload to the recipient in a privacy-preserving manner. So we will have a public bulletin board that can serve as a central database or a public ledger, and then the sender will publish the payload onto this public bulletin board. In order to do so, it will grab the public key from the recipient, use it to generate the ciphertext encrypting 1, attach the ciphertext to the payload, and publish the whole data entry onto the bulletin board. For recipient to retrieve the message, it will then download all those ciphertexts, perform the trial decryption of those ciphertexts, and check if the result is 1 or not. If the decryption result is indeed 1, then this message is actually for this recipient. So the recipient can record all those indices and later will be used to retrieve the corresponding payloads through some cryptographic primitives like here. And in later application section, we will see that trial decryption and fetching process performed by the recipient can actually be replaced by some oblivious message retrieval detection service, or OMR for short. For all the other recipients that is not the targeted user of the payload, they should decrypt the corresponding ciphertext to 1 with negligible probability, which means that they should not receive the corresponding payload as their messages. So for a malicious sender, it could actually launch a spamming attack, which means that it will craft a ciphertext for a garbage payload and force some recipient to receive this garbage payload. And this kind of spamming attack is always possible if you just try to attack a single recipient, because the sender could just grab the public key for that targeted recipient and use it for encryption. However, things can go even worse. Actually, we can have the adversary generate a single ciphertext trying to spam a whole bunch of recipients, which means that those recipients will decrypt the corresponding ciphertext to 1 with high probability, and they will all retrieve and thus process the garbage payload, which is actually meaningless to them. So why this is so bad? It is because in some applications like blockchain, you have to pay something when you try to publish a message onto the public ledger. However, if you need to pay per message per recipient when you try to launch this spamming attack, it's not that attractive to you. But if you only need to pay a single message and spam a whole bunch of recipients, then it's much more incentivized to do so. And on the other hand, for the recipient, For the recipient side, you also need to pay more resource. You also need the bandwidth to download the message, and you also need to have some more local computation power to process the payload. In applications like OMR, things can go even worse. This kind of spamming attack could actually cause overflow, which is a severe crackness issue to the whole system. Fortunately, we do have an intuitive way to prevent such attack, which is to make such ciphertext generation impossible. Based on this kind of intuition, we formalize our snake eye resist property for public key encryption. And why we have this name is basically because in a dice rolling game, we call the event of having both dice rolling into 1 a snake eye event. Because we want our game to be snake eye resistant, which means that the same ciphertext should not be decrypted to 1 by different recipients. And that's why we call our property snake eye resistance. Okay, here goes the formal definition of snake eye resistance for public key encryption. And this is a game-based definition. So the adversary will be given 2 public keys from the public key encryption scheme and generate a single ciphertext. And we say that the adversary will win this game if the ciphertext will be decrypted on the 2 different secret keys into the same message. And the adversary should not win this game with probability more than delta plus negligible. And this kind of definition is actually not directly implied by standard notions like semantic security or key privacy. However, we observe that some kind of public key encryptions are intuitively and trivially snake eye resistant. And in this work, we will specifically focus on lattice-based games because of their post-quantum security, and in applications like OMR, those lattice-based games are actually more suitable to our application need. Okay, so here is the, I think there's something wrong with the slide, but then before we go into the formal proof of PVW snake eye resistant, I will first give a quick recap for PVW. I guess you can see from the background there is something like a PVW ciphertext, and then this is a standard classic encryption scheme that is proposed in PVW07 and also used in the fundamental OMR work, which is LT22. And then for PVW ciphertext, it basically encrypts L bits in a single ciphertext, and then it works over ZT, which is a field. So we have T as a prime. And then for the PVW ciphertext, we have two parts. The A part is a ZT vector of N elements, and then the B part is a ZT vector of L elements. We also have L corresponding secret key vectors, which is here. So each of them is a ZT vector of N elements. To do the decryption, we just perform an inner product with the A vector and L different secret key vectors, plus the corresponding B values. We will have a U vector of L elements. For each UI element, we then do a range check. If the UF value will fall in the range of plus minus beta, then we map the message back to 0. And if the UI element fall in the range of T/2 plus minus beta, then we'll map the message back to 1. For all the other UI values, we just directly map it to bot, which is an invalid message. So the plaintext will be like this, all binary values. We also want to emphasize that the public key for BVW, which is an asymmetric key encryption, can actually be seen as some LW samples. I will explain what is LW later, but please just first bear this in mind. Okay, so now we have a clear side for the PVW recap. And then in LT22, which is the fundamental work of OMR, the authors actually conjecture that the PVW scheme is snake eye resistant, which means that the adversary will be given the public keys from the PVW encryption scheme and then craft us a non-trivial ciphertext, which means that a part of the ciphertext should be non-zero. And the decryption of the ciphertext under two different secret keys should all land into one vector when the adversary wins this game. And we can see that this adversary could trivially succeed with probability 2 beta plus 1 over T to the power of L. Why is that? Because the adversary could just honestly generate a ciphertext under the public key 1. And then if we try to do a decryption under a different secret key, let's say secret key 2, the result is actually a random ZT element before we do the run check. Now, if we want to map it back to a binary message space, the probability of having this random ZT element fall within the range of plus minus beta is exactly 2 beta plus 1 over T. And then since we have L bits encrypted in PVW, this probability will be amplified to the power of L. And in this work, we formally prove that PVW is delta snake eye resistant, where delta is essentially 4 beta plus 1 over T to the power of L. And we can see that if L is superlogarithmic in our security parameter lambda, we will have delta to be negligible. Here we go. Now we will prove that PVW is snake eye resistant, which is also one of our major contributions. And this should be the next slide, actually. OK, here we go. And before that, we will introduce our new assumption, which is LWE with correlation, or co-LWE for short. So in a standard LW assumption, we have a public matrix A. We also have our own secret S. We calculate the B part as A times S plus E, where E is some Gaussian noise. So in the standard LW assumption, we state that the B part should be computationally indistinguishable even given the A part from some random elements. And then in a core LW assumption, we will have two LW instances instead of single one. We have AI, BI, A2, B2, where BI is either AI, SI plus EI, or some random stuff. And SI are our secrets, and EI are some Gaussian noise. So the core LW assumption states that even given some correlation of the underlying secret key, S1 minus S2, those BI are still computationally indistinguishable from some random elements. And in our paper, we do have a formal reduction from the standard LW assumption to our new assumption. So this is not like a fancy magic assumption which I directly assume it to be true. We do have a formal reduction from standard LW to our assumption with some security loss. And now we will prove the snake eye resistance of PVW under core LW assumption. The high-level intuition is that we assume there is an adversary that breaks the snake eye resistance game, and then we will use it to construct an adversary that breaks the core LW assumption. So this adversary will directly have the core LW challenge, which are treated as the PVW public keys, and then it will give us back a non-trivial ciphertext. Together with this ciphertext, the non-zero A part, we will perform a range check with the inner product of the A part and the correlation we have, which is SK1 minus SK2, given in the core LW challenge. It turns out that depending on whether the core LW challenge are some valid LW samples or random matrices, the probability of having this inner top product result falling within the range of plus minus 2 beta are actually different. So we use this probability gap to determine whether we have a real valid LW samples or random stuff in the core LW challenge. So now, we indeed prove that PVW scheme are snake eye resistant. Why do we care about other things? Why do we need to come up with a new scheme? The main reason is that PVW has some efficiency issues. It has a large public key size. It also has a large error range, which will make the ciphertext larger. And in applications like OMR, we just need to define a heavier homomorphic decryption circuit that will harm the application's efficiency. Moreover, the standard module switching is also not possible for PVW, basically because this error will scale linearly with the size of the secret key, although this trick is actually standard for us to maintain the ciphertext size in a lattice-based game. For all the other schemes that is much more efficient than PVW and also suit our application need, like Ring LW and Crystal Kyber, they are indeed efficient, but they are not snake eye resistant. It is because they use short keys. So the keys can come from some ternary or binary or small norm distributions. I will skip the analysis here, but then in the paper we show how to attack all those short key schemes. And all those stuff motivate us to have a new public key encryption scheme that is both snake eye resistant and also enjoyed efficiency as those kind of short key schemes. So here comes the lemongrass, which is our new public key scheme. And we have this name from a snake repellent folklore plant, which is lemongrass without W. And then since we want our scheme to be snake eye resistant, we just call it lemongrass with LW as a prefix. But don't take my word. I don't know if lemongrass is really snake repellent or not. Don't try. OK, here is an overview. It's a lot of stuff on the slide. Please don't try to read everything. I just want to give you guys a high-level intuition. So we will prove the snake eye resistant property for lemongrass based on core LW assumption. And we will also prove CPU security and key privacy with a new assumption also proposed in this work, which is LWE with random hints. And then in the paper, we have formal reduction from standard LW assumptions to both assumptions we proposed in this work. And this is also our major contribution in this work. And into this talk, I will only focus on the construction of lemongrass. And the key generation process for lemongrass is essentially similar to PVW. So we have a public matrix A, and then the major difference is that instead of a fully uniform secret key vector, we will have a hybrid one. The first key elements of the secret key will be SKU. They are uniformly random, and the last A minus K element will be SKS, which are ternary, so they are short. We denote the first part as SKU and the second part as SKS. To calculate the public key, we will just multiply the A part together with the hybrid secret key plus some Gaussian noise, and this will give us the B part. The reason why we have a hybrid secret key is basically because if we have all the stuff to be uniformly random, then we will lose the efficiency as what we have for PW. However, if we make them all to be short, then we don't have the snake eye resistant property. So that's why we want to enjoy the advantage of both games. We just combine them to be a hybrid stuff. So SKU part will guarantee us the snake eye resistant property, and since most of the stuff in the secret key will be ternary, will be short, so we will have efficiency. And then the encryption for lemongrass is also similar to the process of generating some LW instance. We will first sample a short vector X, we multiply this with the public key, and then plus some Gaussian noise, E prime, this will give us a ciphertext of form A and B. Notice that both the public key generation and the encryption process are relied on LW assumption instead of leftover hash lemma as we do have in PVW. So this will give us much smaller public key size. However, if we naively generate all the elements in the noise as Gaussian distribution, then we will have a correctness issue. The reason is that now the ciphertext error is actually E prime times sk plus E times x. So we have E prime, E, x, all as short terms. However, the sk part contains some uniformly random elements. Then when we try to do the multiplication, we will have the first k noise multiplied with the SKU part, which is really large and contaminate our ciphertext. The fix is also easy. We just make the first k elements for the arrow to be 0. And then now the arrow bound will be E prime times sks plus 0 times SKU plus E times x. So all the terms that are not canceled out here are short. This will give us an improved arrow bound based on PVW. And the decryption process is essentially the same as PVW. I will skip it here, and this finishes our construction. And here is a short summary for lemongrass. We proved the snake eye resistant property and also the CPU security key privacy for lemongrass, all under the standard LW assumption with the short secret distribution. And then efficiency-wise, we have a smaller public key size and a smaller error bound compared to PVW. And then we are also able to do module switching for lemongrass, which will, in practice, give us a 2 times smaller ciphertext, depending on your parameter choice. And at last, I want to briefly talk about our applications to oblivious message retrieval and robust encryption. So the high-level primitive for oblivious message retrieval is roughly the same as the motivations we have at the beginning. Instead of having all the recipients perform the trial decryptions and fetching process, we will involve an untrusted third party, which is denoted as a detector. So this detector will help us to homomorphically decrypt all those ciphertexts and then encode the result and send it back to the recipient. The tag also, in a similar way, the adversary can just craft a ciphertext which a garbage payload, and then all those detectors will homomorphically fetch this and then send it to the result for a lot of recipients. So this will cause a severe correctness issue, which is overflow, and that's also why we denote this kind of spamming attack in oblivious message retrieval system as denial of service attack. However, if we directly use lemongrass as the underlying encryption scheme for OMR, then we can have a provable DOS resistance game. And thanks for the efficiency of lemongrass, we can have a faster homomorphic decryption secured for the detector, which is much, much more improved from the original OMR works that use the PVW as their underlying encryption scheme. So since I don't have much time, I will briefly talk about robust encryption. Basically, their definition states that the ciphertext should not be decrypted to all valid messages onto different secret keys. And in our work, we just formally proves that our snake eye resistant definition is essentially equivalent to this robustness up to some small security loss. And our construction also gives the first lattice-based robust encryption scheme that is not following the key or data encryption mechanism paradigm. So that's all for the talk. We refer our interested audience to our full paper, which contains the security proofs and all those reductions and more formal applications, discussions, and some generalization of our snake eye resistant property. So thank you all for the attention. Here is a link for the full paper and also a link for a longer talk. Thank you.
Time for one question, maybe? No?
Okay, thank you. Could you please explain why other schemes like RingLW could not support snake eye resistance? It seems the PVW operations that can support can also be extended to RingLW. Yeah.
Yes. It's actually a really good question. We do have formal analysis in full paper, but then just give you a high intuition. The main reason is that the coefficient for RingLW is highly correlated. So if you craft the ciphertext, you will lose a lot of randomness. You can get some linear equations about the underlying message. And that's why we cannot have RingLW to be naively extended to be snake eye resistant.
Okay, thank you.
Yeah.
Okay, so let's thank the speaker again. Okay, and now we have Ethan Mook, who'll be talking about doubly efficient peer.
Right here, good. Okay. Test. Okay. Yeah. Okay, good. Oh, it's the same. Okay. Thanks for the introduction. As Alex just said, I'm going to be talking about This work is called Black Box Use of Crypto is Useless for Constructing Doubly Efficient Peer. This is joint work with Wei-Kai Lin and my advisor Daniel Wicks. And in case any of you are confused where you are after a lot of partying last night, this is Eurocrypt and the year is 2025. Okay, so as this is the peer session, I'm not going to spend too much time recalling the notion of private information retrieval, but just briefly, so this is a protocol between a server and a client where the server holds some large database that it wants to make public and allow clients to access, and the client wants to access some particular location in this database. And together, they are going to run some sort of interactive protocol. And typically in the peer literature, we think of this interactive protocol as just being a simple 2-round protocol, but for the purposes of this talk, I'm allowing arbitrary polynomial in many rounds. And at the end of this protocol, the client should output the value of the database at the location, at their desired location I. And the main security property that we want is that the server is able to allow this functionality to occur. Well, the server itself learns nothing about the client's input I. And so the main security is that we want this, and the main efficiency property that we want is just that the communication is sublinear in the total database size. And there's one important downside of peer in general that I'm sure many in the audience are already familiar with, in that if, as stated, this notion of peer has this strong lower bound, that the server must touch all locations of the database in order for security to be possible. And so this kind of enforces that the that the server's runtime must be at least linear in the database size. And this is undesirable for many reasons. It's like an exponential overhead over the baseline of if I just did this in the clear, I just asked for location I and the server sent the response. And so to try to rectify this problem, there have been many attempts, or many various primitives that are in this space that try to rectify this problem, but the focus of this talk will be on what's called doubly efficient peer. And so this is a peer where we have, it's going to be the same rough setup, but we're, in addition to this kind of online phase, we're going to beforehand have some sort of offline phase. And in the offline phase, there will be a key generation. The key gets generated somehow, and it's like this one-time generation that is independent of the database and will remain static afterwards. Afterwards, the key will then be used to pre-process the database in some way. And then, using the key, the client can engage the server, and the server now, instead of holding just the database itself, holds the pre-processed database, which can be potentially larger than n in various ways. As before, we want the same security and communication properties as with standard peer. But importantly, because the server is now holding the preprocessed database, the original lower bound no longer applies. And what we can hope for is that the server touches a sublinear number of locations in the database during an online invocation of the protocol. And importantly, kind of for the purposes of this talk, these are the only properties that I'm going to require in order to call something dpeer. Anything sublinear is dpeer. Like anything for sublinear server runtime is dpeer, or server locations is dpeer, and I actually am not going to at all care about the runtime of the server or the runtime of the client. I just care about number of locations that the server touches. Okay, so there are 3 flavors of dpeer that have been considered in the literature at various times. So the first one is called secret key dpeer, and this notion essentially is like the key generation algorithm produces a secret key that the client will then hold, and security is lost if that secret key is revealed. And I wrote this little C box here to indicate that you kind of conceptually should think of this dpeer as the client is the one who does the preprocessing, right? The client does the preprocessing and then gives the server the preprocessed database. Then there's public key dpeer, which is essentially the same, except that the key can now be kind of public, and you can think of many clients as having access to the same public key. Here, I would think of the server as, or that there's like some trusted third party that does the preprocessing and hands the database to the server. And finally, there's this most recent notion of unkeyed dpeer, where there's no key at all, and the preprocessing is a purely deterministic computation that the server can do itself. And so there have been there's been a couple prior constructions that achieve each of these flavors. Notably, in 2017, there were 2 concurrent works that both achieved secret key depeer from this kind of non-standard assumption called permuted codes with noise, or something to this effect. And then those works also essentially showed how to upgrade from secret key depeer to public key depeer using heuristic use of obfuscation. And finally, most recently, in a prior work by the present authors, there was a construction of unkeyed depeer based on the ring LWE assumption. And just to remark real quick, it's not very difficult to tell that unkeyed these notions are, unkeyed depeer is the strongest of these notions and implies public key, which in turn implies secret key. And also, unkeyed depeer itself implies standard peer, because the server could kind of just run the preprocessing each time if it wanted to. But the other two don't seem to imply standard peer, at least as far as we know. And notably, like, standard peer is like clearly a cryptomania object, and in turn implies OT and many aspects of public key cryptography, right? And so this motivates the central question of this work, which is kind of how do these various depeer primitives fit in against the rest of the crypto canon? And where we kind of know stuff about unkeyed peer, we don't know about these other two objects. And importantly, as you might guess, based on the title of this work, this is a lower bound talk. And so our focus is going to be on the weakest version, so that our lower bounds are stronger. So for the rest of this talk, we're going to be focusing on secret key depeer. And essentially what we prove is that this kind of strong, weird conceptual result that black box use of many advanced crypto primitives are actually useless for constructing depeer. And a bit more formally is like, the theorem is, if you have any crypto primitive that satisfies some certain condition, which I'll get to in a little bit, but I'll leave censored for the moment, it's a large class that includes many of your favorite things like FHE and OT and many things, but we'll get there in a moment. And so the statement is, if there's a black box construction of SK depeer from this primitive P, then I get a black box construction of SK depeer from just one-way functions. And so this is like a weird conceptual result that I'll spend a lot of time trying to give you some interpretation for later in this talk. But then also separately, our second theorem is we make some partial progress towards ruling out SK depeer from one-way functions. And so we essentially show that there's no black box construction of SK depeer that has these additional two caveats, that it's 2 rounds and the server is purely passive. Okay, so let's just jump into the techniques for how we prove theorem 1 now. And so the main starting point is we'll start with an SK depeer that is constructed in some idealized model relative to some oracle. And this is essentially how we model a black box construction. And so you'll think of this oracle O sub p as being some oracle implementation of your desired crypto primitive. And so this is our starting point. And the key insight that we're going to use is that in peer in general, there's no hiding property from the client. And so we can essentially have the client run all of the server's code for it and make all of its queries for it, and we'll be just fine. And this insight is heavily inspired by a recent work at last Eurocrypt by Jesko and Mohammed. And so following this insight, we will first compile this starting depeer into one where the server doesn't use the oracle at all. So only the client has to interact with the oracle. And then after that, we will compile from that into one where we remove the oracle entirely, subject to this condition that the oracle is like sufficiently nice in some way. Okay, so starting with this step 1, so our starting point, again, just to make sure that you're all following, is we have this SK depeer that exists relative to some oracle OP. So the client gets to make some queries to the oracle, sends a query to or sends some message to the server. The server can make oracle queries, look at locations in the database, send back a response. They can repeat this for many rounds, right? And so we're going to take this and we're going to compile it into a new scheme where essentially all that's going to happen is that the client is just going to run the original server and client itself in its head. And so it's going to simulate whatever interaction they might have, simulate whatever queries to the oracle they might have by making queries to the oracle itself. But importantly, anytime that this smaller server in the client's head might ask for a location in the database, try to read something. The client's just going to say, hey, server, tell me this location. Send that location to the server. Server will look that up in the preprocessed database, send back a response, and then the rest of the protocol can proceed exactly this way. And so you end up with essentially the exact same protocol, and the communication complexity, notably since the locality, the number of locations that the server touches during the online protocol on the left side is sublinear, the communication is sublinear on the right side as well. And similarly, the runtime of the number of locations of the server remains unchanged on the right side. And notably, we've kind of turned it into this new version of the protocol where the server is kind of completely passive, doesn't touch the Oracle at all, and all of the Oracle queries are on the client side. Okay, so now we've kind of removed the Oracle from the server, and so now we want to go on to this next step of removing the Oracle altogether. And so first I need to kind of tell you what is this notion of nice that I referred to before. And so the definition here is we call it something called a crypto-oracle. So it's an oracle that's of this nice form. It's B to the R, where we think of B as being some just polytime Turing machine that itself has access to a secret random function that only it can touch. So R is some private random function that B has access to, and the only interaction with R that an outside party can have is through B. B kind of gets to mediate how other people interact with R. And so now, if we suppose that this O sub P is itself a crypto-oracle, we're just going to do essentially the same trick that we did before. So if we start with our passive server scheme that we constructed on the previous slide, note that S is passive, and so only prep and the online client will actually interact with this oracle. So they interact with B, which itself talks with some R. And we're going to compile this scheme into, exactly as you might expect, a new prep and a new online client that just runs the old one and simulates the queries that they would make to the oracle by running B themselves. And anytime B would want to query its random function, they'll just use a PRF to make that query for themselves. So that essentially completes the proof of theorem 1. That's essentially, as I said, this is a relatively simple result technically, but it has kind of a weird conceptual flavor. And so I'm now ready to remove this censor bar. This just exists with respect to a crypto oracle. And theorem 2 is a bit more technical, but I think it's less conceptually interesting. So I'm just going to defer all of the proof of any argument about theorem 2 to the rest of the paper. Just suffice it to say that it's adapted from this previous result of Canetti et al. Also, feel free to talk to me offline if you have any questions about it. But I want to spend the rest of my time simply just giving you some justification for why a crypto oracle is a strong object, and then giving you some interpretation for this result as a whole. So first, how strong are crypto oracles? And so I want to show you very strong. They can do practically everything that you'd want. So for instance, VBB obfuscation exists relative to a crypto oracle. The proof is very simple. So we want to have something that has the interface of an obfuscator and an eval function. And so to do this, all we'll do is just the obfuscator, whenever it gets a circuit and some randomness, it will use the random function as a key for an authenticated encryption scheme, send back a ciphertext that encrypts that circuit. Then whenever you get an encrypted circuit from someone making an Oracle query, all you'll do is just decrypt that circuit, check that the decryption works, and send back the evaluation of the circuit. So clearly, this implements the functionality of obfuscation. It's not too hard to show that this is fully secure to anyone who can only make polynomially many queries. And so you easily get VBB obfuscation in this crypto oracle idealized world. And then as a second lemma, we also show that the generic multilinear group model can be instantiated as a crypto oracle. And so in turn, many other crypto objects like OT, FHE can also be instantiated this way. So I just want, this is just some justification that this is very powerful. There are very many crypto objects that can be instantiated this way. And so this kind of leads to this first kind of way to interpret our result is like, well, okay, so the crypto oracles capture a very wide variety of primitives. And so, for instance, if there's a black box construction of skdpr from FHE, then there's a black box construction of skdpr from one-way functions, or from IO, or even from like IO and FHE together. Like it even captures combinations of things, because you can put two things together in a crypto oracle. And you might ask, like, well, what is like a black box construction from IO and FHE? Like these aren't usually black box objects. But our result kind of even captures this notion where you do like run some crypto underneath obfuscation. So you even capture these kind of like, one class of these sorts of non-black box techniques for constructions. And as a second corollary interpretation is we note that our compiler, like these two steps of the compiler, is completely agnostic to any other crypto assumptions that you might have on the side. So for instance, if you have some crypto oracle primitive and you can construct skdpr using that primitive and DDH, then you could have just constructed skdpr with just DDH. But crucially, you need to use DDH over a specific concrete group. So because, as you might expect, like the generic group model can be instantiated as a crypto oracle, so therefore like we need like some concreteness to exist in the world in order to hope for this sort of result. And finally, just in light of the fact that there are positive results constructing skdpr, or various flavors of skdpr from these earlier works and unkeyed dpr, a stronger notion from our previous work, we note that these two constructions kind of crucially make use of some kind of concrete algebraic structure of their assumptions. So in the case of these of Kennedy et al. And Boyle et al., this kind of using the fact that they have security over something that implements a locally decodable code. And from our prior work, we kind of use the fact that the ring LWE ring is conducive to some sort of preprocessing. And this work essentially shows that this type of concreteness is inherent for any construction of dpr. And finally, I'll just pop up my, restate my theorem here and just close with just a couple open questions. First would be just to fully generalize theorem 2, get rid of these two red adjectives. And finally, could we construct dpr from any other assumption? Something weaker than ring LWE perhaps just standard LWE, or something more standard than this like permuted codes with noise assumption. And with that, I'll close. Thank you for listening. The ePrint is available at this link.
Any questions?
It's very interesting work. I just have it's a little bit of a fishing question, but I guess, it's really nice that you have this, large class of primitives that you can model, but yet at the same time, your lower bound is then very simple because you just instantiate where you just replace the ref function with PRF. So I'm wondering, like, what's the core thing that allows you to do that in this setting that wouldn't apply to, like, other primitives that you might want to construct? And I guess it's the fact that they're allowed to have a shared key. That can instantiate the PRF?
Yeah. So I would say it's kind of two things. It's like this shared key, and also like, it's very crucial that we're using the fact that the requirement for communication complexity is the same as the requirement for locality, right? Both need to be sublinear. And so like this whole thing doesn't work for standard peer, of course, because if you ask the server every query, you'd blow up your communication complexity too much. Yeah.
Great talk, thanks. I was wondering, does the notion of a crypto oracle capture primitives that have some kind of like succinctness properties?
So very crucially, let me actually make sure. To some extent, I guess. It's like, if you really like get into the weeds of it, like it kind of depends, like, it shouldn't be allowed that like the server just like, or that like, by the locality property, the server can't just feed the entire database into the crypto oracle or something like this. So it really, all that you really need in order for this to work is this like the total amount of communication with the oracle isn't like linear in the database. And so, but other than that, it can capture whatever you want, like essentially what you want.
Yeah, thanks.
All right, let's thank Ethan again. Okay, and last we have Ling, who will talk about single server client preprocessing peer.
How do I use this? Oh, okay. All right, good morning, everybody. It's a pleasure to be here to tell you about single server client preprocessing, PIR, with tight space-time trade-off. So this is mostly the work of Zhikun Wang, who is a talented master student, but he graduated, so I wind up here giving a talk. All right, so the previous talk already set up a lot of background. Do I get to control this? Oh, no. The previous talk set up a lot of background for my talk, but just very quickly. Oh, okay. So private information retrieval is this problem where the client wants to fetch an entry from a server without revealing which one. Right? Slightly differently from previous works, we're going to assume that the database is a set of n entries of some word size, right? Not necessarily 1 bit, but some generic W bits. Okay, and in the most standard setting of PIR, right, like the previous talk covered, there is this lower bound, right, that says the server must touch all the entries. Right? And the most standard setting is where the server stores the unmodified database and nothing else, and the client stores nothing. Right? And so if we want to get around this lower bound, there are mostly two methods. The first framework is server preprocessing. Right? This is also known as doubly efficient peer, the topic of the previous talk. But this paradigm so far is largely theoretical. Right? The concrete efficiency would not be good. It's going to be even worse than just downloading the entire database or running the linear scan type of PIR. Right? So the second paradigm, right, which is the focus of my talk, is called the client preprocessing. Right? In this case, it's the client who will do some preprocessing on the database, right, to produce some hints. And the client stores the hints and will later use these hints to speed up its future queries. Right, so now our PIR has offline phase and the online phase. Both are interactive. The offline phase, the client needs to privately fetch some hints, which possibly involves downloading the entire database or streaming the entire database in order to create these hints. And then there's an online phase where the client uses the hints to make queries. And so the idea of this paradigm is that after sufficiently many queries, the initial expensive offline phase will be amortized, so we get good amortized efficiency. And concretely, a lot of the works in this space achieves O tilt square root of n client storage. These are the hints the client needs to store, and O tilt square root of n server work, including server computation and the communication between the client and server. But the early works in the space, they have this O tilt, where O tilt hides large polylog or lambda factors, where lambda is security parameter. And once again, if we have too many of these factors, the concrete performance ends up being even larger than linear. Okay. So after a long sequence of works, finally we have the state-of-art schemes. This is a paper we published last year at CCS. We can finally achieve the following efficiency. Client storage is lambda square root n, and amortized server work is square root of n. And there's also a lower bound proven by Kevin Yeo, sitting here in the audience, that shows the product of S and T, client storage times server work, has to be at least omega n, has to be at least linear. So if you compare these two set of results, you see that there is this one remaining lambda factor in the gap. And this is what this talk will get rid of. Right? So today, I'm going to tell you a scheme that achieves exactly s times n equals order n, right? So that matches the lower bound up to constants. Right? And the scheme is very simple. We only need one-way functions, or pseudo-random permutations in particular. Right? And hopefully, it's simple enough that I can explain to you in its entirety in the remaining 12 minutes. OK, so before we do that, I'd like to quickly try to tell you why the prior schemes have a larger client storage. Right? Where does that extra lambda factor come from? Right? Most of them follow this paradigm invented by Corrigan, Gibbs, and Kogan. We call it the CK20 paradigm. Right? Here, the hints that the client stores take on this form. Right? So each hint is basically a parity or subset sum, right, of a pseudo-random subset of database entries. Right? Like here, what I'm showing, the first hint is database entry 3, 8, 11, 15. These are randomly sampled, right? And each hint independently samples random subset of database items and add them up, right? Stores the parity. OK, now to make a query for database item I, the client needs to find a hint whose subset includes this item of interest I. Okay, let's take a concrete example. Suppose the client wants to find database item 9. It looks through its hint. It sees that hint number 2 has 9, right, as part of its hint composition. Right, so it's going to take that hint, and it's going to pull out the indices involved, the entries involved in this hint, but it's going to remove the item of interest from it. And this is the query that is sent into the server. Right? It is important to remove this item you're looking for, right? Because you don't want to directly send a subset containing what you're looking for to the server. Right? So the actual scheme is a little more subtle than this. Excuse me. Okay. But roughly speaking, the client sends this query to the server. The server, all it needs to do is to fetch these corresponding items, right? The ones in the client query, and send them back. Right? Now, because the client stores the hint, which is a parity, right? And the client can now take out, right? Cancel out all the other things from that contributed to that hint, right? And the client ends up with the database entry it is looking for. Okay? So fairly simple schemes. Right? So there's some subtleties that the scheme I just showed you is not entirely secure, right? But that's not too related to this talk, right? So I'm going to ignore that. And also, after the query, clearly the hint has been used. Right? We cannot use it again, so we have to delete that hint and use the rest of the hints. Right? There's also a hint replenish process, right? But once again, it's not too important for this talk. Right? The main takeaway from this overview is that the reason why the CK20 paradigm requires that extra factor of lambda, right, is because of this coupon collectors problem. Right? In order to access a database entry, I need to, as the client, I need to have a hint that includes that entry. Right? And because hints are independently sampled, I need to sample lambda root n of them, such that on average, in expectation, each entry is included lambda times, so that each entry appears at least once, right? Except for negligible probability. Right? Right, so if we store much fewer hints, right, just root n hints, then every entry appears in expectation only once, then there are a large fraction of entries that do not appear at all, right? And then we wouldn't be able to retrieve those entries. Okay, so to try to get rid of this extra lambda factor in the storage, we cannot use these independent hints, right? So we need to go for more structured hints, right? And this is done in a prior work by Lazzaretti and Papamentru, and which also heavily inspired our work. Right? So in their work, the database is organized as a square matrix. Right? So we just write down the database from top to bottom, right, and break it up into square root of n rows. Right? And then we're going to permute each row. Right? So the first row is 0 to 3 permuted. Second row is 4 to 7 permuted. Right? And this way, each entry appears exactly once. Right? And our hints are the column parities. Okay? So now we have exactly square root of n hints. Right? But going forward, I'll just right, the client needs to store this hint table, oops, this side, right, and that can be generated, okay, but in their work, it has to be stored entirely as a truly random table, right, so that the client keeps track of which hint contains which items. Okay. So now to make a query, it's almost the same as before, right? Suppose we want to access entry number 10, we will find the hint that contains it, which is this rightmost column, right? And the client would like to send this as the query, but it needs to redact the item of interest, which is 10, right? Replace it with another random entry from that row. It could be 10 itself, but just equally likely, 8 through 11. Right? And it sends this over. And once again, the server fetches all 4 of these entries and send them back. And again, the client can take out all the other entries in the hints, and is left with the entry it is looking for. Okay. Hopefully, the intuition is pretty clear why this is secure. Okay, so now after a query, the hint table needs to be refreshed. Right? Again, this rightmost column is now revealed to the server. We cannot use it again, right? But what if we want to access the other entries like 3 and 6 in this in future queries? Right? So the solution there is to refresh the hint table by swapping each entry in this consumed column with something random from that row, right? Possibly itself. Right? So after the swap, the hint table looks like that. Right? But of course, now we need to update the hints, right? Because the hint table configuration changed. Right? And in order to do that, we need to download these entries that are to be swapped with the consumed entries. Right? And we cannot go to the server to download these, because then the server knows how we're going to swap them. Right? And that brings to a second, to the other major downside of this LP24 scheme, right? Which is now we need a second server to fetch these swap entries. Right? So these are the 2 downsides of that scheme. 1, we need a secondary server, and 2, the client has to spend linear storage storing this truly random table because it keeps changing all the time. Okay? And that is what we're going to do in this work. Right? We're going to propose a single server client preprocessing PIR using this matrix-style hints, but taking advantage of pseudo-random permutations. Right? Therefore, we will have square root of n client storage instead of linear. Okay, all right, so how do we do that? So step number 1, we will go from 2 server to single server. Right? The idea is actually pretty simple. Right? What we need to do is to have a slightly more sparse hint table. Right? Instead of this dense hint table on the right, right, we will have this table instead. Right? So there are some empty spots in the table. Right? And the empty spots will just be treated as 0, right, or 0 bits, as 0 entries. Okay? Now, after we consume a column, right, we use a column to do access, right, we no longer need to do swapping. Right? We just need to relocate the entries to the remaining, to a random remaining empty spot. Right? So it looks like that. Right? And the column we just used will be eliminated. Right? We won't use it again. Right? Now this time, there's no swap entries to fetch, because we know the entries, right? We know the values of these empty spots, which is all 0, right? And the consumed columns, we just got it. Right? Remember that we send it out as the query to the server. We downloaded these items in green. Right? So we know their values. Right? So we no longer need that secondary server. Okay? And to give you some intuition why this is secure, after we do this, each row stays permuted, right, and among the remaining columns. Right? So after at any point we have a pseudo-random hint table distributed among the remaining unconsumed columns. Okay, and we still maintain the good amortized efficiency because we can support square root of n queries per offline phase, right? And amortized, it's still all the root n server work. Okay, so the next step is to tackle the sublinear storage. Right? Right, so we need to use pseudorandom permutations to track these things, right? And one way to look at it is that we need a data structure that supports the following operations. Right? Initially, we need one instance per row, right? So that initially we distribute the items into random starting positions, right? And then we can look up an item by its value, and we can to locate it where it is. Right? We can also look up by position to see which item lives there. Right? And lastly, and most importantly, we need a relocate functionality, right? To move one item from its current position to an unconsumed random empty position. Okay? And we need it to be space efficient. Okay? And as I said, we'll use a pseudo-random permutation. Right? Here's the permutation, value from 0 to 2 times root n. Right? And the permutation, the first half of the permutation will be used as the initial positions. Right? The second half of the permutation will be used for relocated positions. Right? So I'll stick with that encoding, that color encoding. Right? Initially, we just put the entries according to their P of I, right? Their PRP evaluation. Right? And right? So next, right, let's see how relocate works. Right, so in particular, we will use that latter half, right? M is root n, right? M plus j is the relocated position for the jth consumed column. Right, so suppose we have a query that consumed this column number 1. Right? Where should we locate that entry to? Right, we will check this. We will check this corresponding item. Right, this corresponding entry in the pseudo-random permutation, right, and it says 8, right? So it's going to be relocated to that position number 8. Okay. And this may be a little strange. Okay, and we will store a list and a hash map for all the consumed columns. Right, so this may be a little strange, but we will also relocate an empty spot. Right? What does that mean? Right? So sometimes we will access an empty column because that the item of interest lives in other rows, right? And we will also relocate that empty column according to our pseudo-random permutation. Right? In that case, we will look at the second position reserved for relocation, and it says column number 2. Right? So why does this matter? Right? Because sometimes we may want to relocate an entry, but the relocated position has already been consumed. Right? Just like in this case, we're accessing this entry number 3, right? And we look at the next position for relocation. We see that it's column number 9. That's already gone, right? So we will chase that empty spot, right, which was just relocated to 2. Right? So now 3 will chase the empty spot, right, to relocate to that position number 2. And skip some details, right? But this way we can always find an entry by its value, figure out what is location, or we can look at the location and figure out what entry lives there, right? So that takes care of this relocate and access and functionality, right? And correctness, right? Hopefully should be clear, right? Security, it's same as before. At any time, all of our entries are located pseudo-randomly among the remaining unconsumed positions. Right? And so this way, we have our space-efficient data structure. Right? Notice that we do have to store that list of unconsumed entries, the list of consumed positions, which is the square root of n storage. Right? But it's shared across all the rows, all the instances. Right? So overall, we have root n storage and root n server work, and that matches the S times T equals linear lower bound, right? And the only cryptographic primitive we used is pseudo-random permutation, which can be instantiated from one-way functions. Okay, so just let me very quickly mention the other metrics I kind of ignored. Communication is order T. It's also best among schemes that only use one-way functions, but there are more advanced schemes that can potentially improve the communication, and that's an interesting direction. Right? And second, from a theoretical perspective, PRP is okay, but in practice, small domain PRP are fairly expensive. Right? So if we want to make this scheme truly practical, right, that's a remaining bottleneck to solve. Okay, and yeah, that's the end of my talk. Right, thanks.
Any questions? No. Okay. Well, we're at 10 o'clock, so let's thank the speaker again. And I believe there is a coffee break now.